who wanted to know little more on Twitter, on Facebook, on WhatsApp. They want to know a lot about Moon, Mars, and of course about astronomy. And as I'm talking to you right now, a comet has just zipped past us, and it has moved a little beyond the sun, and it is going to go away from us. It will come only maybe in 6,000 years or so. But the amount of pictures I saw, so many people, even a state like Gujarat, I saw, by no means I'm trying to demean Gujarat. I'm just trying to say that Gujarat is known only for business and other things. But I saw hundreds of pictures coming from Gujarat. So I could see that there is a tremendous interest among young youth, and it is for youth, for those people, I'm actually aiming my talk. So what I plan to cover is, I want to tell you, I want to just start by saying that how will you actually probe, how will you look at the extraterrestrial object? Let's say the ET, extraterrestrial object, is Moon is the nearest object. So Moon is basically some kind of a heavenly body to our grandparents and all. Even to my father, it was kind of a heavenly body. Slowly, the Neil Armstrong thing happened. People started knowing more and more about Moon, and then, of course, the humans landed. Humans have studied. Now, as I'm talking to you, in couple of years, in 2 to 3 years, you will see that you will see humans are actually continuously going to the Moon. There is a program called Artemis program, initiated by NASA. What they plan to do is, before they could go to Mars, they want to go to Moon now. So they are actually preparing an outpost on the Moon, and then they like to go to Mars. So it's amazing that we have studied so much about the Moon. And today's story, I want to draw your attention to what all India has done, starting from a from nowhere. In fact, I'm fortunate enough to have joined ISRO when they were just trying to put pieces together. And I'm so fortunate that I was part of one of those guys who got a chance actually to run an experiment on the Moon. And this experiment was not an ordinary experiment which will go just revolve and look at the Moon. This is an experiment which we did it as we went and fell right on the Moon in a mission called Moon Impact Probe. So I'm very happy that you are all joined together. We are going to learn about this. I'll just take you through a couple of historical issues about how all we want to know about Moon, and then I will concentrate about how do you probe a extraterrestrial body or a heavenly body? How do you probe it? So again, I have to do a tightrope walk where I have to be concerned about very young students, those people who are not expert in this field, and of course there are a lot of people who are seniors. They know this field very well. But for them also, I have got a couple of things which only I can share because I was part of the story. I joined the story in Vikram Sarabhai Space Center, and I did a lot of experiments. So for them, I got a couple of interesting things to tell them. I will tell a lot of details about what are all the ISRO did for Chandrayaan-I. Of course, I have put them in foreign payloads and Indian payloads. Okay, let me just say what is the significance of this. India decided to go to the Moon, but they didn't know what kind of science they want to do on the Moon. In the sense that not that they were completely in dark, they knew fairly what is to be done. But they came up with a fantastic idea. They said that when we are going to the Moon, let us do our best. So they gave a thing called opportunity payloads. They asked the best players in the field. They invited everybody in the world and said that, can you come? We'll give you a free ticket, bring your best instruments to us, and we will do science on the Moon. And it is because of this, out of the 11 experiments which we did on the Moon in Chandrayaan-I, majority of them were from abroad. 6 were from abroad, 5 from India. So I am going to tell you each and every bit about those 11 instruments. So this is where a couple of the children, non-experts may feel little boring, but I'll try to make it very interesting. In fact, I was a bit nervous about one aspect also, that when I give a talk normally in any of the in the hall, I make sure that if some people are dozing, I try to crack a joke. I try to tell them that, well, PSLV is like Sachin Tendulkar. So here I don't even know who is dozing, who has switched off this monitor, who is not at all interested in listening to me. So I have worked around in all this. I will try to bring in a lot of Sachin Tendulkar moments. And I am also going to play a match, just a test match, which the England and West Indies played. So it is for all those youngsters who wanted to know that, well, there is something going to come up. So I'll speak about, imagine a test match being played where there is not even a single soul sitting in the stadium. And the British, the England team played. In fact, they have won the series. They're very, very happy that they beat West Indies. And I was feeling very sorry for the West Indies. They put up a good fight, but they still lost. Okay, let us come back to Moon now. So when we talk about the Chandrayaan-I, so there are foreign payloads and Indian payloads. In there was a fabulous experiment called Moon Impact Probe. This is President Kalam's pet idea. President Kalam said that don't just go to the moon and revolve around the moon. Try to do something out of the world, that is, uh, let us go and embrace the moon. Let us touch the moon. So that is where the Moon Impact Probe came. And I'm so happy that I was part of the Moon Impact Probe. And in there, we had this experiment called CHACE, and it is that instrument which we built. So I'm going to speak about CHACE a lot. And I'll give you an exact idea of how do you actually build an instrument which will go and work on the moon. Of course, I'll take you, then we'll go up to Chandrayaan 2, which is right now, as I speak to you, revolving around the moon, and it is having 13 instruments, out of which 5 instruments could not be, we could not do the experiments. So 8 experiments are there in the orbiter. They are revolving around the moon. So I'll talk about all those 8 experiments which are there in Chandrayaan 2. And then, of course, we are all very much interested that what exactly has happened to Vikram, the lander, which we were all so much concerned about Vikram. So at the end, so I make sure that all those people who are just not so much interested, but will please come back right at the end of my presentation. I'm going to have a very exciting trip, and I'm going to tell you how, what exactly happened. What is the fate of Vikram? Why is the Vikram's fate has happened that way? So we don't know really. We are yet to hear from ISRO, but whatever is there, it's all unofficial. Or is from me, my personal take on what could have happened to Vikram. So the secret is going to be out right at the end. Okay, I'll go. So what I'm planning to do is the following. I will go very, very quickly at a couple of places, and then I'll stop and try to go explain. So I got 2 to 3 places where I'm going to spend 4, 5 to 6 minutes, and I hope I will not bore you. Those 3 places are, I will explain one experiment, which is some kind of a remote sensing experiment. I'm going to take a great deal amount of time for that experiment. It's a moon mineralogy mapper wonder experiment performed by NASA. So I'll talk about that. Then I'll talk about my own instrument where we qualified. I want to tell you, how do you qualify an instrument for taking it to the moon? Number 2. Number 3 is, of course, the fate of Vikram. And in between, I'll be slowly kind of running quickly. So I will try to be running quickly. So if I want to go to, let's say I've given an opportunity for you to go to the moon. This gentleman is just peeping at the moon. How will you perform experiments on the moon is what? Let us see what will you do. There are 2 ways of doing this experiment. One is called passive probing. You just look at the object, and then you don't do like most of the remote sensing satellites which are there, which are not doing anything, just revolving around the moon, and the reflected light, which is actually the solar radiation, which is coming interacting with the Earth's atmosphere. So the satellite, depending on if it looks at the Earth, let's say for some time, just think this Earth is a moon for that matter. So if you just look at the moon, you are not doing anything. You are taking your instruments, looking at the moon. You can do a couple of things. What you can do, depending on the instrument you carry, you can study the near ambience of the moon, that is atmosphere. Moon does not have any atmosphere. So you study only at the surface of the moon. So it's called passive probing. Then you can also do active probing. What you could do is you can send either a laser light, or you can send a microwave radiation, or you can send any other radiation. Actively send your radiation, and the signal which you have sent, that radiation will reflect back from moon, and study that reflected radiation or backscattered radiation. That radiation will carry the information about the surface which it has interacted. So from that reflected or backscattered radiation, you will try to study the object. So this is active probing. In the first probing, you're just staring or looking at the object. In the second, you sent a radiation, and then you studied the reflected or backscattered radiation. So that is called active probing. There is one more thing which you can do. It is in situ measurement. You go right into the action. You be part of the action. Like this guy. This guy is just picking. He has taken his instrument. He's performing the experiments right there, in situ, on-site experiments. Amazing. No, there is nothing more passionate, nothing more exciting than going there and doing the experiment on the site. It is not so easy. It is not possible. We all know that only 12 people have walked on the moon. There are only 12 people who are fortunate enough. After Neil Armstrong, there were 11 more people. Yugan Sarnan was the last guy. After Yugan Sarnan, nobody else has walked. In fact, just sorry to inform you that Yugan Sarnan passed away just very recently, just 8, 10 months ago or a year ago. So you can actually drop instruments, or you can take the instruments right into the ambience. In the case of moon, we sent a moon impact probe. The moon impact probe went and fell on the moon. In that moon impact probe, we carried a mass spectrometer, the instrument which we built. So you could have a sampling experiments, which you could have either a sampling of air. In the case of moon, you don't have any air. You can sample the ambience if you want, or if you carry a probe, the probe will actually study the moon. So that is what mass spectrometer, the CHACE instrument which we built, did. It's an in situ measurement, very, very tough. At the same time, it is extremely fortunate enough to do a on-site experiment. And I'm so happy to be part of that kind of experiment. Now, just like to touch upon a couple of more things about if you want to build a space instrument. I've got a camera, so I have no problem in running this camera. This phone. This phone is very easy. I just run it. Very nice atmosphere, very nice temperature and all. If I want to take this phone, it's an ordinary phone. If I take it to Mojave Desert in California, it will have some problem in running. If I take it to Antarctic, I don't even know the phone will work. So if I want to take it to the space, I have immense amount of problems. I have huge amount of problems. What are those problems, and what are the challenges if I want to take an instrument to the space? The very first thing is it has to be very compact, very small in size, and it has to be weight should be very less. Every gram you carry to the moon, the price is a huge amount of price you're going to pay. So a back of envelope calculation, it just says that $100,000 you have to pay to be able to carry 1 kilogram to the moon. So it's almost 70 lakhs for one kilogram. It almost means one bottle of water will cost you 70 lakhs rupees on the moon. So if the cost of taking every kilogram, every gram is so much, I remember that my project director was telling me that every screw you're tightening, try to reduce at least one screw so that we will gain couple of grams and we can use it in another experiment. So the instrument has to be very compact. It has to be less in weight. And then it has to withstand the radiation. On the moon, you have tremendous amount of radiation. That radiation, and on the way to the moon, as you're going to the moon, you run through Van Allen belt, you run through various radiation ambience. So your instrument has to be protected against that hard radiation. Hard radiation could be very charged, highly ionized particles or other non-charged particles, but carrying a lot of energy. So that's called radiation resistive instrument. Your instrument should be able to resist or to survive the temperature variations. So there's a huge demand for thermal scientists who will protect your instrument, make sure that your instrument should survive and work in the conditions, because suddenly you can't put the instrument right at 30 degrees or whatever. My mobile phone was so happily working because I'm continuously placing it only between 20 to 40 degrees centigrade, very less humidity, and it's just surviving. If you take it to the moon, none of this will work. And of course, to be able to go to the moon, you have to run through the vibration and shock test. That is what your PSLV or your Ariane or any rocket is going to give you. So huge amount of shocks will be given. So you have to survive those things. That is the basic demand you have. Now, what is a payload? So if you're going and revolving around the moon, how does your instrument will work? your instrument will work. And I'm at 500 kilometers, 500 kilometers. So, so if we look at moon right now, we are at 100 kilometers orbit. We could actually, for the case of Mars, we are 470 kilometers orbit. If that is the case, I won't be able to see anything of moon if I'm at 100 kilometers orbit. So I need a telescope. I need a pre-optic which will actually magnify my object. So that is accomplished by a pre-optics, which is basically a telescope. Then the pre-optics will actually magnify the image of my area of interest, and then it will bring it to my dispersive element. So I want to split the light. So I have collected all the light. I want to split the light of my choice, and I could have a grating, I could have a prism. And then after the light wavelength is selected, I can have a detector. And that detector will actually process the data. It will process with the help of electronics, and it will give the data output. So most of the remote sensing instruments will have a pre-optic, which is kind of a telescope, and then the measuring instrument, which will be there. Now, this is just another example. I don't want you to be very much concerned about showing all this. This is basically a telescope which is bringing the light back and then passing it. You can have mirrors. You can see mirror M3, M4, and all. This is not quite a space-borne instrument. I'm just trying to tell you the elements, and with the ray trace diagram, I'm trying to tell you that a telescope would have, and it will fold the light, bring it into a spectrograph, give it to a detector, and the detector will give a signal. Just some kind of a sample hardware which will be there. Don't be antagonized by this kind of picture. This is very simple. Now, let me come back again. Why do we want to go to the moon? And I'm taking you to Chandrayaan-I. Before I take you to the Chandrayaan-I, I want to tell you that humans were always very much on the toes. They wanted to go to the moon. Just within few years of us, they built the rocket, and they learned how to leave Earth's gravity. And Russia was the first to go to the moon. So there was an intense competition between Russia and America. You can see there's a huge amount of competition, and Russia was doing extremely well. And then suddenly it was America who started winning the race. America really, really won the race by sending by landing the human. So landing on the moon, are basically studying the moon in those days, and eventually when India went also, is a symbolic way of saying, a symbolic way of showing your prowess in technological achievement. This is what I strongly feel. You can see that the human has learned this. In the past, there was kind of a race where the most wealthy countries tried all that. And then, of course, apart from the human inquisitiveness, there was also some kind of a rush, some kind of a way of showing it to the neighboring country or to your competing country that you are good at it. So don't take it with very seriously about whatever I'm saying. I'm just trying to say that this is there in human attitude. This has happened in the past. You neither I can change the history nor you can change the history. So there was an intense competition, and it was America which did amazingly well after landing Neil Armstrong, and they had very successful 6 more flights. This is not the complete list of everything and all. I'm just trying to show you how the race took place. Let us come back to our India. Let us talk about our instrument Chandrayaan-I. You can see a huge spacecraft is this. It is no more there. As I'm talking to you right now, Chandrayaan-I is also revolving around the moon. Recently, in one of the experiments of NASA, when they were trying to test their radar, they found out that one object is revolving around the moon, and that's a brain dead object. That object is none other than Chandrayaan-I, which is this hardware which you're seeing right now. It was 1,400 kilograms, almost 1.5 ton, when it was blasted from Sriharikota. When it reached the orbit, it was carrying only 650 kilograms. It's purely because it carried a lot of fuel, which they burnt it on the way to the moon. So it was around 600 kilograms and all. Among the 600 kilograms, only 110 kilograms were given to the payloads, to the instrument. That's why I said that every gram you carry to the moon was very, very important, because how do you go to the moon? You need a rocket. And what rockets do we have? We had only PSLV for Chandrayaan-I. So it was the PSLV which took us, and PSLV is crippled. Our PSLV has got its own capacity to be able to take under 1.5 ton to an orbit from where you can actually take it to the moon. So it is because of PSLV we can no more take 1.5 ton in Chandrayaan-I. How do you go to the moon? I'll quickly run through it because if I spend time, I need to cover a lot of other things about instruments. So normally, if it were NASA could have gone to the moon in one go. Normally, they go to the moon in 3 days. Their rockets are so powerful, their thrust is so good, they can take a couple of tons of hardware to the moon in no time. Whereas for PSLV, 1.4 ton, and then first you revolve around the moon, and then you keep raising your orbit from the spacecraft. You have carried the fuel. So you go to Earth orbit 1. So remember, the PSLV dropped you in a very tight orbit called 250 kilometers by 22,000 kilometers. Then every time you come back to the Earth, you raise the orbit. You fire liquid apogee motor, you raise the orbit. Again, fire liquid apogee motor, you raise the orbit. So you raise 1, 2, 3, 4. 4th to 5th time when you are raising the orbit, you are in very, very tight situation. The amount of fuel you're firing has to be very, very precise. It is at this place, there was a mission called Ranger mission, which ran into a lot of problems. 1961 to 65, America took 9 attempts to go to the moon. All the 6 attempts were failures by America. America learned a lot of hard lessons. We too learned from America. So whatever lessons US had learned, that was all made. We made sure that we will never repeat those mistakes. What are the mistakes? In Earth 4 to Earth 5, if you fire more, then you go into the space. You'll never be able to come back to the moon. In Earth 4 to Earth 5, if you fire less, then the moon will go away. You will never be captured by the moon. So you have to precisely fire the same amount of fuel for same amount of time so that you will be able to reach Earth orbit 5 and be captured by the moon. So in the case of Chandrayaan-I, being captured by the moon itself was a huge achievement. So we got captured by the moon. I was so happy. I didn't get sleep for 2-3 days that whether it will happen or not. We got captured by the moon in a very oblique orbit. Slowly, we brought the orbit back. We were in a polar orbit, 100 kilometers by 100 kilometers. Amazing. So India reaching moon in its first attempt was a great achievement in itself, because the history has taught so many bad lessons to the very big people, the people who struggled. So we learned all that and we are so happy. Now let me just change gears again. We reached the moon and all, and then what science we want to do. So if you just, this is where I'm just trying to say that those are the people who are non-experts. Please pardon me for this. This is very important for all other people, BSc students and all, that what will you like to do? These are the experiments we want to do on the moon. What are these experiments? These are chemical mapping. You can do what all chemical elements are there. Then there are mineralogy. Mineralogy means actually compound materials, which could be many, which could be carbonates, calcinates, and all various types. And so you could do minerals mapping right from your orbit. None of these are actually going and bringing the samples. This is all remote sensing. And it will convince you that just being in 100 kilometers orbit, you can very nicely do your experiment. So you can study the chemicals, you can study the minerals, you can do, just look at the topography mapping. Look at the moon and just take the images. And ISRO had been so amazingly sent one instrument called terrain mapping camera. Stunning pictures. Nobody had ever seen moon the way ISRO looked at it by terrain mapping camera, TMC. These are the instruments. Payloads actually means instruments. I will come back to each and every instrument after this slide. So then radiation environment, you can study what all radiation is coming. Once you're on the moon has got no magnetic field. The solar radiation is all continuously coming and hitting the moon. So you want to study what is happening to the solar radiation which is coming. After it came, the reflected radiation, what is happening? You want to study that radiation. So that is radiation environment. Then magnetic field mapping. You can actually study, is there any minute amount of magnetic field? Is it there? You can study that also. Volatile transport. Since there is no atmosphere, there are particles which will just go, once the particle gets some thermal velocity, it will be lost into this space. So those are called volatiles. So how do the volatiles will behave? You can study them. Lunar atmospheric constituent. So what is all there, even though there is no atmosphere around the moon, if at all it is there, what is there? I'm going to tell you, this is what I worked on. moon impact probe, we carried a mass spectrometer. We studied something which is called nothing. It looks very absurd, but I'll convince you about what is that nothing. Okay, then a small another technical issues where we try to see that all the senior people will appreciate that even though ISRO tried to say in a very humble way that, sir, this is a technology demonstration. We are not doing such a great science and all, but I will assure you, I will guarantee you that ISRO carried fabulous amount of instruments. If you look at the electromagnetic spectrum, if you look at the way they have covered, starting from radio waves to infrared waves, visible, UV, X-rays, and gamma rays. All the way, the entire electromagnetic spectrum is covered by various instruments. So this is the electromagnetic radiation which is being employed by the hardware which has gone to the moon, and they try to probe the moon. It's an amazingly well balanced, very well spread across set of experiments, because of which the Chandrayaan-I came up with flying colors. They also studied charged particles. They also studied neutral particles. The mass spectrometer which we built, my team built, we studied neutral particles. Now, let us go into the nitty gritty. I'll try to go slightly fast. So we carried foreign payloads. I told you that we gave a free ride to 6 instruments, 6 payloads. These are the 6 payloads, and we carried 5 instruments. And the flags which I'm showing here, these are the flags which are we collaborated with UK, and this is German instrument. And then we collaborated with Sweden. This is Bulgarian instrument. And then America gave 2 instruments to us. And we ourselves carried 5 instruments, which is a camera, hyperspectral imager, laser instrument, high energy X-ray spectrometer, moon impact probe. This is all we did. You can see that since we went to the moon, and you could also see that there were 6 instruments, much more than what we carried from abroad. But this is a fantastic experiment, fantastic attempt in which the winner was Chandrayaan-I. Doesn't matter if the foreign instrument has done well, but it was done, the credit has actually gone to Chandrayaan-I. Okay, let's just slightly go through these instruments one by one, and I'll try to explain more on a couple of instruments. You have to bear with me. So it is important now. How do you, what is the X-ray spectrometer? This is Chandrayaan-I X-ray spectrometer. What is Chandrayaan-I X-ray spectrometer? Since moon has got no magnetic field, the intense and the very energetic solar radiation will come, which includes all the X-rays and high energetic particles, which will come and interact with with the lunar surface. And lunar surface, there are a lot of minerals, and it will interact with the mineral, and the mineral will actually get excited because of the charged particle coming and hitting, and then it will give a X-ray. So that X-ray, you can see it from 100 kilometer polar orbit. So the solar rays excited minerals will give out characteristic X-rays. Those X-rays you can study, and you can see on the right hand side I have given sodium line, magnesium line, aluminum line. These are the lines at X-ray energies in kilo electron volts you can identify. So by revolving around the moon, by carrying a X-ray spectrometer, and you can see that which elements are lying on the moon by studying by carrying a X-ray spectrometer. This was built by Britain. Britain are world leaders in X-ray spectrometer, and India actually not only collaborated, they learned so much that I'll assure you that in Chandrayaan-II, we built a similar X-ray spectrometer on our own. Now, India is a proud owner of building their own X-ray spectrometers. Now, let me come back to the smart near-infrared spectrometer. So this is the infrared spectrometer. It's the imaging infrared spectrometer. I will actually go to a next instrument. I will tell you about imaging. I will also tell you about infrared spectrometer. Just bear with me. It's called a multispectral spectrometer covering 256 channels. So basically what you're doing is you are probing, you're looking at the moon, and your detector is sensitive to infrared, visible to infrared radiation. So what is happening is solar light again is everything, the whole thing, the whole solar system, all the planets and all, you are there, I am there, we are all living because of sun. Same thing is happening for our probing also. You can actually study all the moon because of the sun. The sunlight is coming and exciting the various minerals and all. So they will give out the characteristic emission lines in the infrared as well. So we can study them by studying those infrared radiation coming out of the different minerals. I will tell you how it is done. There is a huge amount of very intense amount of development has taken place. I will just run through it. So basically, as I explained it to you some time ago, you have moon, and then you have the space-borne instrument, you have a telescope, and then you have your detector. Same thing is there. If you look at this sketch here, please look at the sketch. So there is a telescope which is actually bringing the light from from moon surface, and that light is carried by fiber optic bundle. And then in this unit, you have a sensor element which is an infrared multi-channel spectrometer, and then that will give you a infrared spectrum from the radiation which is picked from the surface of the moon. So basically, you are at 100-kilometer polar orbit. You are actually looking at the surface of the moon, and how are you looking at it? You're looking at it with the help of having a telescope at the front end. The telescope will actually magnify and bring the small image back to your detector. Your detector will be able to identify what is that light is all about, and you will find minerals which are there on the surface of the moon. And just give you one example of SAR result, that you can see iron oxide when they are looking at some portion of the surface of the moon. This is also iron oxide by using model 1, model 2. This is titanium oxide in the same surface which they have published by SAR 2, one of the images. So just looking at the surface of the moon, you could know that so much of iron oxide is there on this surface. Maybe it could be some kind of a crater's inner place where you have all this iron oxide or titanium oxide just lying there. One more instrument which is amazingly out of the world experiment. The only reason I am not able to actually go into the greater details about this instrument is this is a wonder instrument, sub kV atomic reflecting analyzer, SARA. SARA is an effort by Europeans. It is actually brought to ISRO from Sweden, but one of the detectors was built in Switzerland, and another portion is developed in Japan. So, and then ISRO also played a very important role, where the Vikram Sarabhai Space Center built this data acquisition system. It's a energy analysis, mass analysis detector, which is very small in size. It can do wonders. Actually, the state of art technology which this detector has involved, sometimes it goes beyond my ability to explain, purely because that it involves mass analysis, it involves actually energy analysis of particles. So what is happening is, when the solar light again is coming, interacting with the moon, you can see that this is the moon, solar light has come, and then it will sputter the ions on the surface of the moon. The ions will get sputtered and they will get energy. Once they get enough energy to lose moon surface, they will come out as projectiles out of the moon. Hydrogen also, huge amount of hydrogen, which is a solar flux, which will just bounce back and reflected back from the surface of the moon. That hydrogen also comes out. So you can actually, by studying these neutral particles, which are actually energetic particles, you'll be able to study what exactly is happening to the surface. So it is basically studying the interaction between the lunar surface and solar flux. Solar flux coming and then imparting on the moon, and then the particles which are carrying energy. So you study them. So you analyze their energy also. If you look at this result, this is a mind-boggling result actually. It's out of the world. I mean, people in 50 years ago, they can only imagine that. You can see what is this image says. On the sunrise, on the sunny day on the moon, the solar radiation came, and then it imparted so much of energy. If you look at the energy levels, the white is very highly energetic particles. The towards brown and black and red is very low energy. You can see that from 2 energy to almost huge amount of sub-kilo electron volt energy particles are actually neutral particles going out. In fact, the SARA will be able to say about their mass also, which molecule is this, and then with what energy it is going out. So this is mind-boggling experiment. This was done by the Swedish people. India has got a lot of experience in it. Not only the data, not only the hardware, electronics they built, the lot of data analysis and a lot of that was done by Anil Bhardwaj of PRL, who was in SPL some earlier. RADOM is a radiation dosimeter. It's a very simple, just our cassette recorder, cassette, small, our cigarette box, you can see just pen size dosimeter. It's a solid state detector. It will measure the amount of energy it is falling on it. And it will tell you, it will also has got a spectrometer. It will tell you energy versus how much of dosage it is following. So if you just see, look at this particular graph, you can see that it is given deposited per channel ionizing radiation, which is basically in gray units, GY, which is joules per kg. How much of energy is being imparted on the solar surface, and those energetic particles which are coming, they will intercept through the radome, this particular one. So as the energy particles are there just falling through it, it will measure that energy. So it will give you the dosimeter as it is in different orbits, 1,000 kilometer, 2,000 kilometer, as the dosimeter is just like if you go to Baba Atomic Research Center and all, most of the scientists are carrying a very miniature detector which will tell them about how much of radiation they are exposed to. So this is the energy analysis. It will give you energy versus intensity also. It's a spectrometer. Whereas the BARC scientists are, if you are going to a place where a lot of radiation is there, you can carry a small dosimeter. It will tell you how much of energy it has fallen on you. A lot of people who are there in X-ray, in the X-ray diagnostic centers, they also have the dosimeter, something like that, but with energy analysis. Now, foreign payload, mini synthetic aperture radar. This is a synthetic aperture radar. This is an active payload. This is active payload where you're actually sending a microwave wave radiation, and it's a polarized radiation, and you want to study the radiation which will come back. So what you do is you are sending a right circularly polarized radiation, and then the one which will come back from the moon could be both left circularly polarized and right circularly polarized. That from that radiation you can measure a parameter called circular polarization ratio, CPR. So there is a CPR which you build. This circular polarization ratio is actually will be able to tell you what type of particle is there. Particle roughness will be there. And indirectly, you will also be able to refer to coherent backscatter opposition effect, CBOEE. So if you know coherent backscatter operation effect, you'll be able to see whether there is a ice. Now I'm interested in knowing about ice. Why am I interested in knowing about ice? If you look at the moon and sun, moon has got a very small tilt and it is revolving around the earth. So there are a lot of regions on the North Pole and South Pole which are dark, permanently dark, and that part of the moon has never seen any sun at all. It is all dark. So the only way to see, and it is conjectured that there's a lot of permanently dark regions carrying a lot of buried ice which is there for billions of years, which is actually water. So if you can probe these microwave radiation, you can actually study whether there are ice reserves or there. It is always conjectured that in permanently shadowed region in North and South Pole, there is huge tons and tons amount of ice which is buried, and people are interested in studying about it. So if this mini synthetic aperture radar, this will work in 3 modes. I am not actually a microwave expert, but I can still tell you that you can actually have only a S-band mini synthetic aperture, which will just tell you where the ice is there. You can have both S-band and X-band, which will give you double confirmation that yes, there is a ice, and much more confirmation is by a way called bistatic, coordinated bistatic measurement, where one radar actually shoots the microwave radiation, the other radar from another which is situated on the other spacecraft. In this case I'm explaining here, Chandrayaan-I and Lunar Reconnaissance Orbiter, LRO. LRO is right now existing, it is revolving around moon. So we can actually do an experiment with Chandrayaan-II, where from Chandrayaan-II, I will send my LCR, my particular microwave radiation, which is circularly polarized, and then the other radar will pick up, and that is bistatic mode. It will have a much better opportunity to confirm that there are buried ice on North Pole and South Pole. This is one of the very important experiments. There was a gentleman called Paul Spudis from NASA. He struggled. He worked very, very hard. Very sad to inform you all that he is no more among us. But he's the man who fought for to prove the theory that there is water on the moon. Moon Mineralogy Mapper. I just saw the clock. I saw that I'm going very, very slow. I like to go fast, except this particular payload. This is one of the out-of-the-world experiment carried out by Brown University and in conjunction with Jet Propulsion Lab, NASA, Moon Mineralogy Mapper. This instrument goes on to discover water on the moon. And the way this has been there, I want to just take 3 slides to explain you what this experiment is all about. This is the ultimate technology which anybody could have. So this is called multispectral imaging. So it is not an ordinary imaging. In fact, it's a step beyond multispectral imaging. It's called hyperspectral imaging. What is hyperspectral imaging? You pick up radiation from the surface and then you collimate it, bring it and give it to a, here I'm just coarsely showing actual as if it's a prism. But I have a state-of-the-art grating. This particular grating is called E-etched grating. It's having all optical compensation and all. And then it will do dispersion of the light. And it will do dispersion of the light not only from one plane, it will give from both the planes. So it will actually image. So if I just if I take this setup will give me not only the surface information, it will give spectral information around that surface. And I'm interested in that. So in the past, what we were doing was, if we have a camera, we have only a 2D camera where I just get the picture, the intensity, total gross intensity. Then if I put a filter, one single filter, I will get a information about that space at one wavelength. If I put 2 filters, I get 2 or some 10 filters, which is called hyperspectral. Multispectral. Multispectral is I cannot have innumerable filters. The innumerable filters you can have them by having a state-of-the-art grating here. That grating was built by NASA, and that is responsible for creating a out-of-the-world detector called hyperspectral imager, and the name is Moon Mineralogy Mapper. And normally, just try to explain a little bit more also, same thing. So this is where I'm actually picking up radiation in a remote sensing way. I'm having a dispersing element. Then actually I scan it. You see that there's a scanner here. In fact, if I have a grating which can actually do all the 2-dimensional dispersion, I don't even have to scan. The scanning is only to actually scan in surface. I don't need it at all. My special grating will do. And that is what this hyperspectral imaging is. That is, if I am having a surface here, can you see that surface? If I pick up this surface, you can see that you have all spectral information which is going bottom in X, Y direction. So I can go to a place, I can pick up a small location, which could be crater. I can build up this spectrum at that crater. So I picked up that crater and I got the spectrum. And how do I do it? And this is the spectrum. I will be able to say whether it is calcite or whether it is kaolinite. I don't know what are these names. These are various calcium-based or iron-based, titanium-based, what type of radiation I have. So this is the spectrum. So in one go, I don't have to do anything. In one go, I'll be able to see all the spectral information I can collect. And how do I collect it? I will collect it by this wonder baby called M3. M3 is such a small instrument, but it has, let me just try to explain to you what exactly it is, this instrument. From telescope, the light has come. The mirrors are folding the light. And then with the help of a baffle, the light has come to a grating. This is the grating. It is multifaceted, convex, multifaceted, blazed, electron etched beam grating. Amazing grating. This is the wonder of this particular instrument. And then, so the white light came and dispersion has taken place, and that has come to a detector, very, very special detector. And that detector will actually, a 2-dimensional detector with all going from almost half micron to 3 microns. It has to be cooled and all. So it's a state-of-the-art detector, state-of-the-art grating, and this is evolved over a period of time. This instrument was lying with NASA to be sent to Mars. And then India was so lucky that the one which is actually catching dust in their shelves was given it to India, and we carried it in Chandrayaan-I and got those fabulous results. This is the ultimate thing. From moon, the radiation is coming, and the mirrors are folding it back. This is the grating, and you can see that the dispersed light carrying all the information in 2 dimensions are bringing back. This is order selecting filter, and then it is a MCT detector, which is 400 nanometer to 3000 nanometer. That's what it is. Amazing. Just show you one example of M3 data. So M3, you get this kind of a cube where you not only you get the image, you also get the spectral information. So I'll show you A, B, C. A is one of the crater which is brilliantly lit. B is a background. C is some kind of shadow region. You can see that near the rim of the crater, there is a lot of spectral information. On the background soil, there is no spectral information. In the dark area, there is no information. In fact, they have checked it at Earth also. They looked at the Earth. You can see that when they looked at the Earth, the moon mineralogy mapper revolving around the moon looked at back to the Earth, and then they built the spectrum of the Earth. You can see when they looked at the cloud or when they look at the water, they look at the surface. They got the classic. This is, I mean, you cannot have calibrated, or you cannot have proved that your instrument is a wonder. This is a classic example that your instrument is wonder. They proved it by looking at Earth. This is the Earth image, and this is the spectral information of Earth in one go. They get it in one shot. That is what it is. Okay, I'll come back to Indian payloads. I've almost got 40 minutes. These are the payloads where terrain mapping camera 6 kilograms, hyperspectral imager 2.5 kilograms, lunar laser ranging instrument is there, I think 11 kilograms, and then hex, another spectrometer, X-ray spectrometer 14 kilograms, moon impact probe 32 kilograms. Very important for me. Every gram is important. And terrain mapping camera built by SAC Ahmedabad. Fantastic instrument. Never ever in the history of the moon anybody has looked at the moon at 5-meter cartographic information. I'll show you the picture. If you look at the picture, your eyes will be stunned at the pictures, how we got it. First time in the history of looking at the moon, nobody has looked at the moon at 5-meter resolution. Nobody. First time Chandrayaan was seeing. And it is done by a very simple optics, very robust optics, built right here in Space Application Center, and and having a cartographic imaging where at each position you actually collect the light in 3 channels. So this is called to be able to build the cartographic image, you have to have 3 channels. These channels you can see, this is the nadir weaving, this is the fore weaving, this is the back weaving. The swath is 20 kilometers, and then you collect the radiation. So you collect the radiation. This is where it is all seen. This is some kind of a 8-element optical system which is doing both telescope as well as imaging. Both it is doing at f.4. F4 is a large throughput optics, and it is giving good amount of light, and then you can actually see a very weakly lit areas on the moon surface. But the best part is cartographic part. And the chip which they selected was lying in ISRO, because it's a space qualified chip. Those days when Chandrayaan was getting ready, the India was under the thing called the US Department of Commerce has banned. We were under the banned list of R&D centers, and we could not take any instrument from any hardware from abroad, especially from US. We were banned. So whatever chips they had from Europe or from their friendly nations at that time, those chips were used, and a very simple optics was used. And then you can see first time cartographic imaging. Of course, they had built it in GSLV and in remote sensing cameras and all. Your deep space one, first time effort, they came up with flying colors. And who else can get a better picture of this? Have a look at this picture. Amazing picture. Look at the 3-dimensional effect of this particular crater. How beautiful is this crater? You can see there are craters within craters. This is the floor of the crater, 5-meter resolution. This is the rim of the crater. And look at this picture. This is the historical site where Neil Armstrong has walked. This is the site where Neil Armstrong has walked. This is the site. You see the huge mountain, this kind of the sandy mountains, which you will see in the Apollo images. This is taken by terrain mapping camera. 5-meter resolution, 20-kilometer swath. Amazing. abilities. Similarly, you can also find something called lava tubes. These are the tubes where lava has flown, and these are the place where you have actually some kind of a tunnel. You can go and live in this tunnel. Because a lot of radiation comes on the moon, you go there. It's a 2 kilometer long and 0.36 kilometer wide. So you can almost build a huge lab. Don't have to worry about the cosmic rays, those things, and all coming on the moon. You can live there. So this has picked up terrain mapping camera. Hyperspectral images. I'd like to go a little fast because I'm really running out of time. So hyperspectral image is built at SAC again, Indian payload. It is having 64 bands, and the wavelength region is 420 to 940 nanometer. Again, looking for minerals, infrared imaging spectrograph, multispectral, not hyperspectral, but reasonably good. It has worked. It has shown its metal. You can see that one of the craters, they have picked up this cube. You can see the cube, which is a spectral cube, and then they took out 750 nanometer albedo, and from there they'll be able to estimate where all titanium is there in this particular crater. Very good job. Hyperspectral imager, built by SAC, worked extremely well. Another experiment which ISRO had zero experience, absolute zero experience, they built it. Thanks, I mean, my salutes to the LEOS team, LEOS in Bangalore. They have to learn about a guy who is with the MTech degree, who did a lot of work. Of course, there were a lot of people who were project directors and deputy project directors and the senior guys who designed it, built it, and all. But the lot of hard work was done. I mean, a lot of the hardware development was done. I didn't mean hard work. Hard work was done by everybody. So the hardware development was done by that MTech guy. I'm not getting his name now. So what you do is actually you shoot a laser to the surface of the moon, and then you collect the reflected light. So you need a laser, very powerful laser, to shoot the light. You need a telescope to be able to collect the light, and then the time delay which is taken for the laser light to go and come back is proposed is given will give you the information about the altitude. It is so accurate that with 5 meter accuracy, you'll be able to collect the light. So as you're revolving around the moon, there are a lot of gravitational anomalies. Your spacecraft will get a jerk, a little bit of jerk you will be able to get. That jerk can be measured because you are carrying such a very good 5 meter resolution. You can also build a lot of topographic reconstruction. I'll show you one Schrodinger basin, very famous basin near South Pole, where they have taken, you can see that fabulous topographic image is constructed by Lunar laser ranging instrument. First time the chance was given to the people at ISRO, they built it, came up with flying colors. This is a standing ovation, my standing ovation to the scientists and engineers of ISRO who built LLRI. Amazing. So let me wind up Chandrayaan-I. So we spent around 380 crores. What did we do? The Moon Impact Probe carried actually the flag which went and fell on the moon. And we found moon is hydrous right on the science. It went the results for M3, Moon Mineralogy Mapper, the NASA sensor. Spectacular 3D images we got at 5 meter resolution. 5 meter. Prior to that, we had only 100 meter resolution. Mineralogy at 100 meter resolution. Global effort. First time, nobody had ever tried the way we did it, like taking people to the moon. We are at par with the leaders in space. This actually offered the step to go to planet Mars. And let me go to Moon Impact Probe. Moon Impact Probe, I think I'll cut down a couple of other stories. President Kalam, actually, it was his idea, who came to the meeting and said that go and send a probe to the moon. It is because of him the probe was there. This is the probe which was part of the Chandrayaan-I, which got separated from the spacecraft, went and fell on the moon. This is in a way an active experiment, you can say. So this is how it is done. You were in the 100-kilometer polar orbit, you got separated slowly, and you got spinning also. It spun and went, had an impact at South Pole. It took 22 minutes. It is in this Moon Impact Probe, I built a spectrometer, mass spectrometer, which actually measured, sampled the environment for 22 minutes, and the instrument is all over. Once it fell on the moon, it's all finished. That's what the experiment is. So there was a color camera. We took a lot of pictures as we were falling down 25 kilometers above the moon just before the impact, and we found out where exactly we fell. The Moon Impact Probe fell very close to the South Pole, where Shackleton crater is there. It is near Shackleton crater, where the US is going to build their base in a couple of years now. Now, let me come back to this instrument. Spend another, I'll try to cut short it because I'm running out of time. CHACE is the instrument we built. What is CHACE? Chandra's Altitudinal Composition Explorer, CHACE. It's a mass spectrometer built at Space Physics Lab, Vikram Sarabhai Space Center. These are the people, my team members. I'm so happy to show all my team members. These are the people who my boss, Sridharan, always called them dare to dream. We had zero experience, absolute zero experience. Sridharan said that you dare, you dream, just dare to dream, and things will come out. And with that, we people, MTech in electronics and Pradeep in electronics, Tirtho in microwave engineering, Neha from MSc Physics. These are the people who had zero idea, including me. Sridharan had little bit of idea about flying a mass spectrometer. I'm basically a radiation spectroscopist. I'm a UV spectroscopist. But we learned all the tricks of the trade. We built this hardware. I will not go, I'll not spend too much of time. There are a lot of things are there. I'll run through them. We wanted always, we had this aim. This is the slide which I'm carrying for the last almost 13 years. This is whether water is there, we always wanted to see. We wanted to see whether helium is there. And this is little more into details I will try to avoid. Challenge was to be able to build an instrument which is 10 raised to minus 10 torr sensitive. So we have to build an instrument which is very, very sensitive enough. And how do you build it? We build it by characterizing. First, you want to see whether the instrument is capable of measuring 10 raised to minus 10 torr. Then make it very strong, rugged, and then make sure that your data acquisition control is working. I'll tell you what it is. Then you have to do this thermo vacuum test, vibration test. So if you cross all these Lakshman Rekhas, then I felt as if I'm standing in Mount Everest. To be very honest with you, as I'm talking to you, my hairs are raising and I'm feeling very excited that I ran through all these steps and I built this baby, which is a flight model, which is no more there. It has fallen on the moon. I am saying from 9th floor, I can see moon every day, right at the south pole of the moon. This instrument has fallen. Nobody can take this credit away from me. It is an immense feeling, amazing feeling. So we did the characterization. We made sure that 10 raised to minus 10 torr. In the Earth's atmosphere, 760 torr is there. You remove 10 orders of magnitude of pressure and see whether it will work or not. The instrument is very, very sensitive to work even 10 raised to minus 10 torr. And then over and above the 10 raised to minus 10 torr, if there is any particles which are there, we will be able to see. When Sridharan made this presentation in the very beginning, a lot of other seniors in the group, they ridiculed Sridharan. They laughed at Sridharan. They said that what are you trying to do? You're wasting 3 kilograms of weight. But it is Sridharan's gut feelings that no, I want to make sure, I want to see that 8 to 10 raised to minus 10 torr, there will be some volatiles. There will be some particles which will come out. There could be water which will be just wandering, very small amount of water. These are the gut feelings of Sridharan, because of which the CHACE actually was approved in Moon Impact Probe. And I was handpicked from Institute for Plasma Research, Gandhinagar, to Vikram Sarabhai Space Center. And why was I taken? I knew how to actually do these experiments. I knew how to create vacuum. I knew to work with experiments and all. And it is for that reason I just jumped over to the VSSC opportunity and then worked there for 5 years. And mechanical reinforcement. The instrument is so fragile, it will just break, because when you take a 22G ride in PSLV, your instrument will never survive. So we have to do a lot of mechanical hardening. So how do you do it? There are a lot of ways. This is a mechanical engineering problem. All of us turn into mechanical engineers, and we learn from infrared sensing satellite heritage. There is a heritage which is lying in ISRO. They will tell you if something is just not working well, if something is radiating more, then there are solutions available in ISRO. All those solutions. So this is called heritage. We followed all that heritage, and we were so thankful to the back support given by ISRO. It is because of them, it is for them in VSSC, in a lab called Space Physics Lab. We built this instrument under the guidance, under the supervision of ISRO. The CHACE instrument was built. There was a problem, one more serious problem, where all of us turned into a hacker. The girl whom you saw, Neha, turned into a hacker. purely because we wanted to know what is happening between the instrument and the computer. We want to remove the computer. Otherwise, you can't carry a computer. It's a very sophisticated instrument. So computer was removed by actually involving a serial sniffer software, and we did some kind of reverse engineering. And then whatever data it was going from the computer that was captured by this software, put it into a FPGA, a programmable gated this thing amplifier, FPGA, and put all the programs in there, remote the computer. And then we stuck that particular chip to the sensor, and it started working. And we had a power supply also separately. So what did we do? We did thermo vacuum test. We did vibration test. Mind-boggling test. I wish I would have spent time, lot of time. I'm running out of time. This is very, very important Lakshman Rekhas you have to cross. My story would have been amazingly interesting if I had explained about vibration test, thermo vacuum test. You have to call it. What is vibration? Your instrument will be vibrated to very large amount of vibrations. The instrument has to survive. What is thermo vacuum test? Your instrument will be kept in a huge chamber and air is removed, and you have to supply the power, and temperature is varied 0 to 60 degrees. This is what you see in the moon. So you're creating the conditions of the moon. You're creating the conditions of the PSLV, making sure that your instrument will work. If your instrument failed, it's gone. My instrument failed 13 to 14 times in thermo vacuum test. In vibration test. I didn't care. I kept on coming and improving, coming and improving. And then I qualified it for 30G test. So from a instrument which I procured it somewhere, which was a commercial kind of thing, I ended up having a space qualified instrument. And it took me 5 years. It took us around 4.5 years where we built, we turned it into a space qualified instrument, standalone. It will take the data, it will give the command, it will take the data, its power supply, everything is all on its own, and it will work on its own. This is what was all done in building an instrument like CHACE. And after 4.5 years of all my experience, just before handing over to the mission people, this instrument is there in my lab. It's a flight model. I am not supposed to be holding it this way. I was just going from one center of ISRO to another center in Trivandrum. I had not slept for 3 days, so I just had to take bath. I took bath and got this picture. This is not even an official picture. And we built one. So where does this instrument stand? I wish I could have spent more time. This instrument is almost, I could have explained everything here compared to all the best instruments which went to probe the Earth's atmosphere, which went to moon, which went to the Jupiter and Saturn. Our instrument is 100 times better dynamic range, 10,000 times better sensitivity, and weight-wise, it's very small. I'm really running out of time. I have to go quick. So I'll cut short this. We published our paper, and there were some issues and all. And I'm very proud to say that the science journal, which has published actually the moon mineralogy data, there you can see that I have written a letter saying that the CHACE was the first instrument to see water on the moon. The credit should be given it to us. The science journal did give the credit back to us. It is here. I want you people to see it. If you happen to, you can Google. I've written a blog on this. So even though the credit lies with M3, we were the people who saw the water 3 months before M3 was even operational. Chandrayaan-II, I think I'll quickly go through. I got 10 minutes, and I hope Shekhar will give me 10 more minutes. So Chandrayaan-II is all because Vikram lander, Chandrayaan-II is all there. But apart from Vikram lander, the Chandrayaan-II orbiter, as I'm talking to you, Chandrayaan-II orbiter actually has carried 8 instruments. Those instruments are revolving right now as I'm talking to you. I'll tell a bit about those eight instruments. I'll switch over to Vikram then, and then I'll wind up. So the challenges are many. I'll not go into the challenges. I will run over. It is all Chandrayaan-II took a ride on Bahubali. This Bahubali is all those people who are trying to sleep. Please wake up. This is an amazing rocket. It is Mark III GSLV avatar of Mark III. Almost worth of 375 crores, just one rocket. And its power is immense power. If any of you guys are awestruck by Airbus A380, its power is lifting. The thrust of this GSLV Mark III is 4 times Airbus 380. You can't imagine the beast, the amount of power it has got. Just if A380 is actually taking off, the whole airport reverberates. The GSLV Mark III is so much, 4 times, and you have to control it, send it to the orbit of your choice. And it's amazing. That is why it is called rocket science. I wish I could have spent more time on rocket science. I'm not a rocket scientist. I want you people to appreciate the amount of power you are carrying. It is not an ordinary Deepavali, some kind of firing this thing. This is not that rocket. This is a huge. And of course, the Apollo rockets are almost a few dozens or few 50 times more powerful than this Bahubali. So what are we doing? We are carrying an orbiter. We are carrying a lander. The lander will have a rover also. This is how they look. The lander is at the front. It will get separated once it is revolving around the moon. Then the orbiter will be orbiting. The orbit is orbiting right now also. And how do we go? I will not spend time much, just a minute here. So we went very, very slowly because the GSLV Mark III put us in one orbit. Slowly, 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 we raised the orbit. And then we got into lunar insertion orbit. And then we got captured by the moon. Again, same problems, whatever persisted in Chandrayaan-I. You make any mistake, you could have never gone to the moon. Everything went off very well. We got captured by the moon. We started revolving. So 28 days to go into the lunar insertion orbit, 11 days to reach, 11 days to circle around the moon and make a polar orbit of 100 kilometers. From 100 kilometers, the lander will get separate. And this is where the scene starts. The lander will get into another orbit called 100 kilometer by 30 kilometer. From 30 kilometers, it will actually try to go and land on the moon. So there are three stages. First, take off from the Earth, get captured by the moon, and then get closer. So the lander got closer by 100 by 30 kilometers orbit, and then it is going to land. The orbiter has got 8 experiments. Just highlights, just another 5 minutes, I'll wind up. The Chandrayaan experiment, the X-ray spectrometer is a imaging spectrometer built here, right here in India. There was some kind of a total gross X-ray measuring instrument called solar X-ray monitor. Then there are a dual band, L band, S band synthetic aperture radar, which can actually look for the buried ice on North Pole and South Pole. And then it can look for buried ice actually means water. Imaging infrared spectrometer, first time built by ISRO for Chandrayaan-II. And then terrain mapping camera 2 is a miniaturized small camera, again 5-meter resolution, amazingly, same thing is there, it's capturing the images. CHACE-2 is the sister of CHACE-1. It is looking little more than 100 atomic mass units, slightly larger, 3 times larger atomic mass units. There are 3 more instruments. So there are totally 8 instruments which are all built in India. In a span of 10 years, everything is built in India. Can you imagine India can do this? Built all the 8 instruments right here on our soil. Wonderful. I mean, so then lander rover, this is the lander rover actual picture. The Vikram lander rover is actually Pragyan coming out somewhere in, I think in Bangalore, ISAT. So the lander would have 3 instruments. One, two, if the lander had actually gone and they landed, it would have had opportunity to study whether there are any seismic activities on the moon. The moon is dead. Seismically, moon is dead. There are no moonquakes, just like earthquakes. But still, there are some microquakes. If at all they are there, they would have studied. Thermal properties of the soil, one instrument was there. Langmuir probe was there, which was to study when the astronauts were walking on the moon, there was a lot of charged particles which are actually getting captured on their suits. So they wanted to study what kind of charge is there by carrying a Langmuir probe. 3 instruments on the lander. 2 fantastic experiments on the rover. One is called laser-induced breakdown spectroscopy. LIBS, nobody has ever seen it in India or in ISRO. They built it for the first time. Then alpha particle X-ray spectrometer. Yeah, fantastic. Both of these are active. In LIBS, you're shooting a laser, trying to see what type of radiation is coming out. In alpha particle, you're shooting alpha particles. So there is a curium radioactive metal which is taken, which will actually give a lot of alpha particles. These alpha particles will excite the nearby samples and X-rays are emitted. Those X-rays you measure. Wonderful instrument. These are the state of the art. Only few countries in the world have built it. India has already built it along with them. If these had worked, we were rubbing our shoulders with any of the space power. Unfortunately, Vikram landing took issues. These are some experiments they did. I don't want, I'm not here. I'm running out of time. I want to hold my time. I don't want to be stopped. And these are all landing sites and all. Chandrayaan-II, Vikram wanted to be land here. They want to land here, right at the South Pole. And if you look at, this is the Lunar Reconnaissance Orbiter recently sent a picture. This is the pink spot is where they wanted to land. You make any mistake, look at the dirty terrain where it is there. So it is almost saying that where eagles dare. They wanted to land here. Yeah. Anything? Yeah, another 3 to 4 minutes. 3 to 4 minutes. So landing, I wish I could have gone more into the landing. I will not go into the landing. I'll just tell about only official statement which came from ISRO. Annadurai gave a presentation where he said that rough braking will be there, precise braking will be there. And then whatever I'm going to explain now, I'm warning, please warning. This is nothing official. It's all from me. It's personal Makbul Ahmed's views. These could be absolutely wrong also. Please ignore it. But I just picked it from various discussion groups and all, where a couple of ex-ISRO people narrated, discussed those things I'm saying. Times of India carried a fantastic article where they said that first the rough braking will take place from 35 kilometers to 18 kilometers. From 18 to 7.4 kilometers, precise braking will take place. Then there is the absolute navigation phase, ANP. And then they had a fantastic way of avoiding any kind of eventuality and land from 400 meters, from half kilometer. They had every other way to land. I will avoid all those ways, absolute navigation phase. I'm going to take time, but they had everything in place. Everything should have worked. But unfortunately, what do we know officially today now? Times of India reported that while trying to tilt the Vikram from horizontal to the vertical landing, the applied brakes have overdone and hence the tilt, and then it hard landed, is what Times of India said. Government in Lok Sabha said that extra braking caused the deviation and hence there was an issue in landing Vikram. Let me tell you, this is my take, what could have it happened. Normally in rough braking, there are 5 engines. Among the 5 engines, 4 in the corner, 1 at the center. So in rough braking, all the 4 engines will be firing. And so there's the retro firing and they are pushing. So this is called power landing. So when you're actually landing, you're already having a huge amount of 6,000 kilometers per hour speed with which you are piercing towards the south pole of the moon. And then from opposite side, you're firing these 4 engines, you're stopping. So you stopped it by rough braking, firing 4 engines. Precise braking is to switch over to 2 engines. I may be wrong here, but this is what was said on the many discussions. So these 2 engines, if you misfire a little bit, then you can tilt. The tilt could have taken place. It is this tilt which could have happened as per all the people we were watching live at 2.1 kilometers. When they switched over to precise braking, the tilt took place, and then we didn't know where exactly the Vikram went, but indeed it has crash landed. Vikram has crash landed. That is all we know. Thank you so much for your attention. I stop my presentation here. Thanks a lot again.
Thank you, sir.
And just like to show my anybody wanted to contact me, this is my email. Please, these are the mail and these are my blog details. I think on request they may send you these details also. You can note down also. I think we can have discussion now. I'm done.
Yeah, thank you, sir, for the wonderful lecture. I asked my colleague Pallavi to read out the questions.
Yeah.
So one question is, why ISRO declared the mission say 95% success? What is the meaning of this number? Specifically for Chandrayaan-II it is.
Yeah. I'm very sorry. It is actually a very controversial kind of stand one would like to take. I put forth, if Pallavi could actually know that I put forth all the efforts which were made by ISRO in Chandrayaan-II. That is, you made an orbiter, okay, you made a lander, you made a rover, everything you made it, everything you went there. There were so many problems you could have faced, all the problems you resolved. You went there, you happened to have one of the experiments of landing and doing some experiment. So it is all up to you to say how much of percentage of success you have got. I would not like to make any statement. The 95% success was made by none other than the chairman of ISRO. So not that I am trying to just keep quiet. The Everything is in front of you. I wish if ISRO had made a public statement about what has happened to Vikram, and more information would have come, it would have been much better. But I think, in my view, that number is just, it is just a number. It's up to you to decide.
Yes, sir. Thank you. Actually, it is a question, so I read it. But we know what all ISRO has been done. It's tremendous.
Yeah.
And all of you, whatever you have did.
Thank you.
Okay, the second question is the moon. Why the moon does not have a magnetic field, although it has a molten core just like Earth?
Yeah. Okay. The magnetic field presence need to be there depending on the composition of the core. I am not a geophysicist. A geophysicist will be able to give you a correct answer. That is, even though you have core, but the core composition is what? It got to be more iron oriented. So that particular iron only would be leading to a building of magnetic field is what I believe. I could be wrong. I want the student to actually to confirm it from an expert. Good question though. Very good question.
Uh, yes, sir. Some more question which might have
Yeah, yeah.
already answered during your talk, but I'm still reading it. Why Chandrayaan took 48 days while Apollo took 4 days to reach the moon?
Yeah. Is it, let me just, I want to show you this. Yeah. Is it seen by the viewers now? Yeah,
Yes,
okay,
sir.
great. So anyway, so it all depends on Saturn V rocket and GSLV Mark III. Saturn
Yeah.
V is a very powerful rocket. Saturn V's thrust is almost 50 times more than GSLV Mark III. So in one go, if you just follow my arrow, in one go, it has given so much of thrust to this parking orbit of this Apollo landing module and the control module, that in one go it will be able to reach moon and then it can revolve around the moon. Whereas the GSLV Mark III will never be able to take it. It doesn't have so much of thrust. It is to do with the thrust of the rocket.
Okay.
So
So,
Saturn V versus GSLV Mark III. Yeah.
okay.
There is a very good article which is written by Times of India and also in a couple of other places. They
Yes.
can Google and read the exact numbers of Saturn V and GSLV Mark III.
Yeah, one more question again related with the landing only. Is there any possibility to test the small landing before landing our main lander, or means can we prototype landing?
Yeah, okay, very good question. Very good question. Our problem is the following. The problem is, what is landing? Landing is actually the landing which we tried is called a retro firing landing. It's a power landing. Retro firing actually means you need to have thrusters which will actually fire in the opposite direction of the velocity and it will stop the opposite velocity. There is no way you can have, if it had been an ordinary parachute like you do it in Mars or in some places where atmosphere is there. There is no atmosphere on the moon. You are going with tremendous forward velocity. You have to retro fire it to be able to stop it. So I don't see any other way of just testing for the landing and then sending the other landing thing. No, you have to do it with all preparations on your hand. Very good question though. Amazing. Good thinking.
So one more question. This is related with the career in ISRO. Do the physicists have opportunity in ISRO, or is there any department of physics where physicists can work?
Okay, the Physical Research Laboratory in Ahmedabad, PRL in Ahmedabad, Indian Institute of Space Science Technology in Trivandrum, Space Physics Laboratory in VSSC. These are the R&D centers of ISRO. I did my PhD in PRL Ahmedabad. Similarly, I worked in Space Physics Lab. Indian Institute of Space Science Technology is a academic institute only to train science and engineering students who will go to ISRO. So all the students can look up to doing projects in these three institutes.
Yeah. One more. It was actually at very initial stage the question was come. How to find what type of the elements present in the moon, at the moon surface or in moon?
Yeah. I think in my presentation, it was amply clear that we can do various type of experiments,
Yes.
such as we can look at the X-rays which are emitted from the surface. We can look at the visible light. There is not much of information buried, but the infrared radiation carries a lot of mineral details. So by looking at the reflected light of the sun from the lunar surface, you'll be able to tell what minerals are there on the surface of the moon.
Uh, yes, sir. And one more with the SAR, that is synthetic aperture radar. It
Yeah,
is, can it work even at night time and map the surface of Earth
exactly.
also?
Exactly. Yeah, yeah. This is actually meant to be working only in the night, or doesn't matter to it. These are microwave radiation. It will just penetrate through. Even it will penetrate through clouds and all. It will get very good pictures of our cities, towns, and all the satellites which we have built. So night is just a no problem. 24/7. Just go ahead. It will work. In fact, okay, the more importantly, the most important part is the synthetic aperture radar is actually meant to work in a permanently shadowed regions, bring the information about that region where the sunlight has never ever reached from the day of formation of that particular crater.
Uh,
So
yeah.
amazing it is.
One more again related with the science education. How we can develop a human capital, especially in the field of education, in science and technology.
Yeah, it's a very general question,
Yeah, it's a very general
very
question.
difficult to say. But I just want to I want to respond to it this way. When I give my presentation, a lot of people ask that how come that you spend 400 crores for Chandrayaan 1, or let us say another 400, 800. The Chandrayaan 2 cost is around 1,000 crores. Just the PS Mark 3 itself was 300 crores. So what are you getting back in terms of the money you have spent? You are getting a lot of trained manpower. You are getting a lot of people who can tomorrow have their own startups. I think the present government scenario where they are encouraging a lot of startups to do it, it's all amazing that it will give you back in the form of technological know-how. You can do wonders. Yeah.
Yeah. Okay. One next one, sir. It is again with the career options. What is the opportunity or role a civil engineer can have in the field of ISRO? Maybe regarding to the soil studies or something like that.
Yeah. Civil engineering. Yeah, as far as getting a job in ISRO for civil engineering is concerned, there are little bit few opportunities are there where they want to build their own uh, their own infrastructure on Earth. So, but not really for the space missions. I don't see. I don't see. Mostly electrical, mechanical, computer science.
Yeah.
So, and of course, communication.
Yeah.
Civil, I don't see them participating in the space mission.
Yeah. One more, sir, again related with the Vikram lander, was the heartbreaking issue, a software glitch. That is, heartbreaking is due to the software glitch which caused this kind of a hard landing.
For
According
Vikram
to
landing,
you, uh, uh, it is related with the Vikram lander that hard landing, whatever happened, is it a software glitch? Any opinion about it?
absolutely no idea. Zero idea. Absolutely zero idea. I don't know. I only gave a possibility in which the uh, the uh, the firing of two engines could tilt it, because it was said that it is tilted. So I'm sure the ISRO people knew that they were anticipating this tilt would take place. Then accordingly they can control. These are controllable firing thrusters. These are not ordinary thrusters, just like Diwali you switch on and then they will go. I'm sure they
Yeah.
knew it very well. Whatever explanation also I gave may be absolutely wrong. So I don't really know what is the exact reason.
Yeah. Uh, Another question is related with the future plan. When will Chandrayaan 3 be happen? Or what will, when it will take place? Chandrayaan 3.
Yeah. Since I'm not connected to ISRO, but I've been hearing only from news channels and all that Chandrayaan 3 will just go in a year time, which is almost, I think if this pandemic had not happened, I think Chandrayaan 3 would have really moved fast. Never in my life, starting from my PhD days in 80s, I saw even a satellite development would take 4 to 5 years and all. A space based probing will take place within 1 to 2 years, but it was declared, and I'm quite excited, kind of amused also that that they will go so quickly. They will go very quickly. landing. They'll make a landing attempt. No idea though.
Okay. Okay. One question related with the fuel of the rocket, maybe a bit controversial. That sending rocket, do we are spending money or very limited? It is more precious or very limited resources available on Earth, like fuel.
What is the fourth and fifth you said?
It is related with the fuel. That are we actually spending the money is a bigger question, or the limited resources of fuel available on the Earth which we are using is a bigger question or
Uh,
more concern.
one is money. Second one is what you said.
It is fuel,
Fuel,
whatever we are
fuel.
fuel, whatever we are
Okay, fuel.
using.
Okay, okay,
Yeah.
fine, fine, fine. Yeah, 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 yeah. Yeah, yeah. I think it's a trade-off between fuel is not a problem. Money can buy a fuel for you. So, what is the question? I didn't get the question exactly.
Actually, the question is towards the fuel resources. Is it necessary so we are actually exhausting the fuel resources? So can we change that to some non-conventional
Okay,
or
okay, okay,
something like
okay,
that?
okay, fine, fine, fine. Oh no, I think if I'm not mistaken, this is a very, very intelligent question where they are trying to say that the present fuel, there is a thing, there's a number called per kilogram of fuel you carry, this much of thrust it will give. So there is a big debate, not debate, huge research is going on where can you find capacity of thrust. So that is one way people are looking. That's how we move. One moves out from solid fuel to liquid fuel and to a very fascinating fuels which will give more thrust. That is one aspect. Regarding the money, if I'm not mistaken, a small satellite, CubeSat of 1 kilogram, people spend almost lakhs of rupees to just not in India, abroad. They spend tens of lakhs of rupees just for launching a 1 kilogram satellite. So when you want to play a game in space, money is not, you should not be, you can't really save money. You
Yes.
need to pour money. But I'm not saying that you need to be lavish and waste money. But the money involved is huge. But the fruits you get will also be huge, very limited. Like nobody can take a claim of India being the only and the first country to reach Mars in its first attempt. I mean, how amazing it is.
Yeah.
Just a good state, not only a good statement. Tomorrow, our people can sit down and build hardware for a Mars landing if Elon Musk wants to land tomorrow. We can, a lot of sensors can be made in India. People who worked with me have immense amount of knowledge.
Yeah. Thank you, sir. Actually, question might have not properly framed. The questioner want to ask about this cleaner fuel only. That more than money, the limited resources are concerned. That is what is the meaning. Okay. And now another one, that can we use a nuclear fuel as a efficient fuel?
Yeah, nuclear fuel is actually being used. It is being used for a couple of rovers. They used it. Nuclear fuel is actually, there's a treaty among all international community that nuclear fuel should not be carried to the space. So it is not very easy to use nuclear fuel. Nuclear fuel is used only if you're going to external planets such as Jupiter, Saturn, and all. But for routine experiments, there is a consensus that please don't use nuclear fuel.
Okay. Thank you, sir.
Yeah.
These all are the most of the questions. If there is anything on YouTube, Shekhar sir.
No, they're not much any on YouTube. So I think we have few comments here by Koraksha. Discovering water on moon was one of
Yes.
the foremost achievements, and it's worth the mission money was we spent. So I think with this, thank you, sir, for the wonderful lecture.
Thank you.
Everybody lost track of time. Uh, so I would now call upon Shamla madam again to propose the vote of thanks.
Hello.
Yeah. Yeah.
Yeah. Okay. So, sir, I'm here for the most pleasant job of the day. It is my pleasure to thank our today's speaker, Professor S.M. Ahmed, on behalf of IIPT Mumbai Sub-Regional Council. Sir, we are very fortunate that you accepted our offer and gave us detailed picture of planning of Chandrayaan-I project and the analysis of the study done with this project. Your presentation gave us clear idea about the ability of extreme hard work and guts the scientists like you have. We all are grateful to you for giving us your views about the fate of Vikram, that is the latest project of ISRO. I take this opportunity to salute all present and past scientists of ISRO. We are indebted to the management of KJ Somaya College for allowing us to use their platform for this program. We admire all the members of the Department of Physics at KJ Somaya College for the efforts they have put working together with Mr. A. Shekhar to make this program successful. We are very much thankful to them. All the participants have shown faith in us, that is in IIPT Mumbai Sub-Regional Council, by being here with us. You have given us confidence in conducting such programs. Sincere thanks to all of you. Thanks to each and every person who helped making this webinar an enjoyable session. Back to Shekhar. Thank you.
Thank you, madam. Yeah. Thank you, sir, again for the wonderful lecture. Okay.
Loved it. Yeah, enjoyed it.
Yeah.
Yeah. I
Thanks.
hope it was okay, I think.
Yeah,
Yes,
sure.
Yes,
So it
sir.
was a
enjoyed it.
wonderful lecture. So, anybody wants to add anything here? Those who are there as guests, our guests.
Korak is from
Hey,
US.
doc.
Korak
Yeah,
had
yeah.
joined from US. Is
Hey,
Korak
Dr.
there?
Ahmed.
Hey,
Yes.
Korak.
Hi.
Ah.
Hi. Yeah. I mean, I'm sorry. I received the invitation quite late, so
Oh, I'm
I
so
couldn't
sorry. Yeah,
inform you. But
sorry.
it
Was,
was really a pleasure always to listen to you. I know we have spent enormous time together talking about. I still remember that picture of yours in front of doing the vacuum test. I remember
Dude,
that lab.
thank you.
and our enormous coffee discussions on those days. Yeah, but thank you for this
Yeah,
beautiful talk. Yeah.
I must say thank you. I
we
am
are
sorry. I just
thank you
told you
joined
so
us
late.
at the
Yeah,
short notice.
yeah. I was busy, kind of busy preparing. So I'm sorry for that. Yeah. But yeah, amazing. You made it. That's fine.
Yeah.
Okay.
Thank
Fine.
you, sir.
Okay, so
Thank you.
thank you very much.
Yeah.
Santosh, I think now you can end the meeting.
Yes. Okay,
Yeah.
sir.
Yeah.
Yeah, sir. Okay.
Bye.
Okay. Bye.
Bye, Korak.
Bye.
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 Bye, everybody. Bye, everybody.
Bye.
Thank you.
Thank you, sir.
Thanks again.
Thank you.
Thanks again.
Thank you.